A result called the Bloch theorem is the next key step in understanding the quantum mechanics of crystalline materials. This is a very important mathematical simplification for crystalline structures. It turns out that just because we assert that the potential here is periodic, we can draw a general conclusion about how we can write the solutions to our Schrödinger equation. We can draw this conclusion even if we don't actually know what the form of the potential is. What we're able to do is to separate the problem into two parts. One part describes the behavior that is the same in every unit cell. This part is somewhat like a generalization of the states of individual atoms or groups of atoms in the unit cell. The second part describes global behavior of the wave function over the entire crystal. This approximate separation leads to our entire way of describing the quantum mechanical states of crystals in terms of what is called a band structure. There are two presumptions to derive the Bloch theorem. First, we presume that the modulus squared of the electron wave function is periodic with the lattice periodicity. This presumption is straightforward given the one electron approximation, since we regard this as a measurable quantity. This electron density quantity is essentially the local charge density. As we mentioned before, next we're going to presume that the electron wave function obeys these periodic boundary conditions. This presumption is to some degree a mathematical trick, but one we can get away with under a broad range of circumstances. For simplicity, we'll start here with a one-dimensional version of this theorem. Then we'll generalize to 3 dimensions to deal with real materials. If we take this single value requirement that we came up with before, that is, this idea that the wave function at point x and the wave function at point x plus na, which is having gone all the way around the chain, should be the same, and we then combine it with this second condition that we have imposed on ourselves, that the charge density or the probability density has to be the same in each unit cell. So if we move over by an amount a, we will get the same charge density or probability density. And that, we deduced, implied that the wave function at position x plus a had to be equal to the wave function at position x times some unit complex number. Then, putting these together, we conclude that the wave function at position x and the wave function at position x plus na must also both be equal to this number, c to the power n, times the wave function at position x. We have moved along successively, adding on a every time, and we've done that n times, and every time we did it, we had to multiply again by this unit complex number. So we presume, therefore, that the wave function at position x has to be equal to c to the power n times the wave function at position x. In other words, c to the power n has to be equal to 1. This condition allows us to simultaneously have this equation hold and also this one hold. So that means that this number c has to be one of what are called the nth roots of unity, and there are n of those for some particular capital N. And these are the numbers that, when raised to the power capital N, equal 1. And there are n such numbers, such distinct complex numbers. If you take any one of these numbers, where s is an integer between 0 and n minus 1, and raise it to the power n, you will get 1. So this is a standard result in complex analysis. It's actually quite straightforward, and you can check it for yourself. You could also check by example that there are no other distinct complex numbers for which this is true for a particular choice of n. So substituting using this result we've just written down here, where s is one of these integers, and substituting that back into this expression gives us that psi of x plus a has to be e to the I ka times psi of x, where k is one of these values. So that's a simple conclusion that we get from this equation here with this substitution in it. Now, this form, c being equal to e to the 2 pi I s over n, where s is one of these integers, is mathematically common for c, for writing down c, although it is not technically unique. Now, the numbers that we get, the set of numbers we get, are unique, but this is not a unique way of writing them down. We could choose any consecutive set of capital N values of this integer s and end up with just the same set of possible values for the numbers c, just written down in a different order. Remember that for any integer m, e to the 0 is the same thing as e to the 2 pi is the same thing as e to the 2m pi. All of these are just equal to 1. So the values for c would just keep cycling round if we kept on increasing s beyond this. We could keep on increasing s. It's just that these new numbers that we came up with would in fact also be the same as the numbers that we had come up with previously for earlier ones in this list. It's a cyclic behavior of c as we keep on increasing s. We can therefore end up with correspondingly different sets of values for k. All of these are equivalent. And instead of writing this as a set of possible values for k, with s going all the way from 0 up to n minus 1, it's much more common conventionally to use this symmetric list instead. So we have k is 2 pi n, little n, over big N times a being the repeat length, where now we let n be any of these values, 0, plus or minus 1, plus or minus 2, all the way up to plus or minus n over 2. Now, to be absolutely correct, there's an error here. There's one too many values in this list. And we should omit one or other of the end values. We should omit either the plus n over 2 value for little n or the minus n over 2 value for little n. These give you the same answer, and hence we should omit at least one of those. This just happens to be more convenient to write down, and for large crystals, this does not cause us any problem. If we end up really working with small objects, we actually have to be much more careful. Note, incidentally, that it makes no difference in our expression here if we add 2 pi m over a to k, where m is any integer. The set of allowed values of e to the I ka that we get just remains the same set. So we can use this set of values, or we could even use any set of values like this, where we've added on e to the 2 pi m over a. All we're really doing is reordering our list of possible values of k. Now, this has a specific significance later on in what are called extended zone schemes. So there are many equivalent ways of writing k, and in fact, they're periodic. So, for the Bloch theorem then, we have the first statement of that, which is the following. This is what we have just proved. The wave function in a one-dimensional crystal with n unit cells of length little a can be written in the form that the wave function psi of x plus a is e to the I ka times the wave function of point x, subject to the condition that k takes on one of these values, remembering that formally actually we should eliminate one or other of these two n values. This is a statement of what's called the Bloch theorem. And what it's telling us is that if we have a periodic system, then there's a specific condition we end up with on the wave functions that would be solutions in any such periodic system. And that statement is going to turn out to be very useful. Note in this expression here that these k values are exactly evenly spaced, and they're spaced by an amount 2 pi over the length of the crystal, because the length of the crystal here is capital N times little a. When I say length of a crystal, of course, that's a somewhat loose expression. It certainly is the length of our loop here. Technically, a mathematical crystal would go on forever, but we are approximating that infinite crystal with a loop instead of finite length. And this is true regardless of the detailed form of the periodic potential itself. No matter what the form is of the periodic potential, it's always true that we can write this expression for the wave function. It's always true that the wave function at a point a further over is e to the I ka times the wave function at the point x, where k can take on one of this set of values here. Now, while that is a correct statement of the Bloch theorem, it's actually not the way that we mostly think of the result of this Bloch theorem. And there's an alternative statement that's entirely equivalent that has a somewhat simpler way of visualizing it. So, take our expression that we just proved, this is essentially our Bloch theorem here, and multiply it by e to the minus ik x plus a. So we multiply both sides by that. So, multiplying the left-hand side, here we put in the e to the minus ik x plus a, and on the right-hand side here, multiplying by e to the minus ika simply cancels that out, and so we're left with an e to the minus ikx over on the right-hand side. Hence, if we define a function that is what we have on the right-hand side here, we call that u of x, we will have that u of x plus a is equal to u of x. Because this here, if we call that u of x, then what we have on the left is u of x plus a. Everywhere we have x here, we have x plus a on the left-hand side. So that means that this new function we've just defined is periodic with the lattice periodicity. It's just a mathematical function, but we've proved that this function is exactly periodic with the lattice periodicity. Another way of stating that is to say that u of x is a function that is the same in every unit cell. Rearranging what we have here simply gives us that psi of x is equal to u of x e to the ikx. That's a simple rearrangement of this statement here. Now this has quite a simple visual meaning. So we have an equivalent statement for the Bloch theorem. The wave function in a one-dimensional crystal with n unit cells of length a can be written in this form, where u of x is the same in every unit cell. And as before, our possible values of k are subject to this condition. And again, strictly speaking, we should leave off one of these two. Now, these two statements are exactly equivalent. We derived the left statement here from the right one, and it's easy to derive the right one from the left one. From the left form here, we have that if we go to x plus a instead, so we just substitute in x plus a all the way through here, well, we know that this was the same thing here as what we have on the right-hand side here, because u of x is equal to u of x plus a. So we can replace u of x plus a here with u of x. And then we can go on. We can simply take the factor e to the ika out of here and put it at the front. But then that is just saying that this expression here is the same as e to the IKA times psi of x, because this is psi of x. And this expression here is simply the right form. This form here is psi of x plus a is equal to e to the IKA times psi of x. So we've derived the right form from the left one, and we derived the left one from the right one. These two expressions are exactly equivalent in their mathematical implications. But the new form we've written, the second form, the one we had on the left, makes it clear to us that there's a way of visualizing what's going on here. And here I'm plotting just the real part of the wave function to make this a little easier to see. This is the form of our wave function solution, perhaps for some specific kind of potential. The specific form of it is not so important, but what we have drawn here is some function that's the same in every unit cell times an envelope that is basically a propagating complex exponential wave. And we can think of this then as an envelope function, multiplying the unit cell function u of x. So for different problems, of course, we will get different solutions. But whatever the solutions that we get for any of these periodic problems, they will always be able to be written in this way. A unit cell function that's the same in every unit cell times an envelope where the k can only take on specific, discrete, and evenly spaced values. That's what the Bloch theorem really means. So without knowing anything about the actual potential we have here in our crystal, except that it's periodic, we are able to deduce that whatever the solutions are, they take this form, an e to the ikx type of envelope multiplying a unit cell function that's the same in every unit cell to get a total wave function that might look, conceptually at least, something like this.